Okay, we're all set? Can you hear me? Yeah, okay, thanks. Okay, so welcome back. If this is your first semester, welcome to UF, whichever one. This is EML 6934, optimal control. So I just want to get through a few preliminaries. I just got the listservs for the class like late last night because I requested them yesterday morning and they took a long time for them to email. So I'm going to email the entire class, the syllabus. It's a website. I'll do that later this afternoon. But basically, the class consists of a bunch of assignments. They're all on the website. There are 2 exams, a first exam and a second exam, and there's a project. Each of the exams is worth 30%. The project is worth 40%. Okay, the way this class works, this is not like a lot of classes that you may otherwise take. This class is really largely going to be about you and not about me, meaning that whatever you get out of this course is going to be what you put into it. I'm going to provide you a framework to be able to learn optimal control, but in the end, this is not about like you sitting there struggling to worry about, oh, how is this going to affect my grade? How is that going to affect my grade? That is not, if you're in this class for that reason, you're taking this course for the wrong reason, all right? This class is about learning optimal control. And I'm going to provide you not only the framework, but if you have questions and you have other things that don't necessarily have to do with specifically what we're learning in the class, but maybe related to what we're learning in the class, like you might be doing some research where you may feel that optimal control might be something that would be of use to you. These are the kinds of things I have no problem if you want to come to my office and you want to discuss these things with me, because that's what this class is. This is a PhD level research class. It's designed so that you can not only just learn the technical details of what we're actually going through in the course itself, but also be able to utilize it in things that you're going to be doing outside of this class. So don't feel limited to just what's in the class. Okay, now if you come to me and you say, I've got some really cool application and it's in economics, don't expect me to be an expert in economics, all right? But I mean, if it's an optimal control problem or something similar to an optimal control problem, we can certainly go through it and we can talk about how you might solve it and how you might analyze it. All that kind of stuff is fair game for this class, all right? So it's important that you just keep in mind that I'm not structuring this class as a you take an exam, you get a grade, and then you go on your merry way. That's part of what we have to do, but it's not exclusively what we have to do. And the project is the biggest part. It's on the website. Well, like I said, I'll email this to you in a little bit later today. The main thing about this project is I'm not giving you the problem. You're going to have to come up with a problem on your own. I give you parameters that tell you what category the problem has to fall into, but beyond that, everything else is entirely up to you. I give you a couple of sets of guidelines as to how you need to go about trying to formulate and solve the problem, but if there's a problem that's of interest to you in some area of research, whether it be biomechanics or whether it be aerospace engineering or robotics, I don't care what it is, then that's the problem you should pick for your project, okay? Don't wait for me to give you the problem. You need to start thinking right now about something that you can do, because the project is due at the very end of the semester. So this is not about spend a week and hurry up and do a project, okay? I want you to think throughout the semester, what kind of problem can I do? What would be tangible and manageable? If you need help trying to figure out, is this problem going to be possible to do in the amount of time that I have to do it in this class, that's the kind of stuff I'm happy to talk to you about. I'm happy to even learn about why you want to do that particular problem, and anything I can do to help make it possible, that's good too, okay? The textbook for the class, and again, unlike a lot of courses, this is not the universal book on optimal control, okay? Everything you need to know about optimal control is not contained in the 452 pages of this book, okay? This is a guide, all right? It happens to be a very good guide. That's why I picked this book. I really like this book a lot. There are 3 reasons why I like this book. One is it has a good presentation of the mathematics, but it doesn't overdo the math. There are a lot of optimal control books that are so theoretical, but by the time you're on page 7, you need you need 7 PhDs in math in order to figure out the first chapter of the book. And then by that time, you will have spent 20 years trying to read the first chapter, and you won't even get to the second chapter because you don't understand the first chapter. All right, so that's not a good book for a class like this. This is an engineering class. We need to have something that's tractable. That's the first thing I like about this book. The second thing I like about this book is the examples in here are good in the sense that they are comprehensive and cover the material without going overboard. They're not such complicated problems that you're looking at them and saying, I just have no idea what this guy's talking about. And it doesn't make any sense to me. And the third thing I like about it is this book is extremely inexpensive. This is, I think, this actually says $26.95 in the USA, but I think you can get this book for like $12 or $13 if you look on Amazon.com. New, not used. It's a really inexpensive book, and it's a paperback. It's been used for a long time. It was written originally in 1970, but a lot of the stuff that's in here, you think, well, that's really old, like it's 40 years old. But it's actually a very accurate representation of the subject of optimal control. There are other books, by all means, that if you want to go consult other books, I recommend a couple. The two that I actually really like are these, and you can go get them. First one is by Bryson and Ho. It's called Applied Optimal Control. And it's published by Hemisphere Publishing. Hemisphere Publishing. And the second one is a book that kind of takes sort of the opposite extreme of this book, which is that it does every single special case. And it's actually it's still a really good book, but it's a lot more mathematically, dense than this one, which is by Athens and Falb. And it's called Optimal Control, an Introduction. It's a good book, but it can be a bit overwhelming. This is also Dover Publications. This actually was originally published by McGraw-Hill, but it was redone by Dover Publications, I think, in 2008. This one is 1975. And they're both good books. Bryson and Ho's book is again, these are all, the reason I picked these books is because they're classic books on the subject. They are not expensive. You could buy all three of these books for probably less than $60 because Bryson and Ho's book is less than $20, and Athens and Falb is probably $25. They're all paperbacks, so they're, and the thing I like about Bryson and Ho's book, it probably has the best set of examples of any of the optimal control books, but it has the absolute worst notation. I mean, absolutely the worst notation. They'll just dream up symbols in the middle of problems, and you won't have any idea what the symbol means because they will have introduced it right then and there, and you won't have any idea why they used that symbol as opposed to some other symbol. But the examples are absolutely stellar. There are some examples in there that you will not find in any other textbooks on optimal control, and it's really good for that reason. So if you're looking for really good examples, then Bryson and Ho is a really good book. If you're looking for something that has more of a feeling of like real hardcore theory, then Athens and Falb is a good book. I think that my personal feeling is that you can learn a little bit more directly out of this book when you're studying examples. This is more of a good reference to have for later on, okay? And this book is kind of a combination between those two. So, but it doesn't have as many examples. That's the main. If there's a criticism of this book, I think it's just that. It's just it doesn't have enough problems. But it does have quite a few, but the other ones will supplement that. Okay, but I don't want to assign too many books for the class, as people don't want to go buy lots and lots of books. Okay, in addition to that, I've got my own course notes, which will also be on the website, so you can download them. I only ask a couple things about the course notes, is that you can use them, please use them for whatever you want to use them for, but if you find a typo, and there may very well be typos in there, please let me know as soon as you can, because I will fix it and I will upload a new set of notes, because I don't want there to be typos in there. But inevitably, I wrote those notes myself, so there probably will be some typos in there. I fixed a number of them over the years, but it's not complete. The notes they've got all the basic framework in there, and and I have some examples, but the other stuff will supplement that. Okay? So let's just, today what I want to do is I want to talk a little bit about what this class is about. Because I've taught this class twice, and twice before. And each time I find, the second time I noticed it more than I noticed it the first time, that students fundamentally don't really understand what they're doing in this class. They do the math, and they're like, okay, math. I have no idea what I just did. Okay? That's not good. That's not what this course is supposed to be about. So we have to start from a point that everybody feels comfortable. And I thought a lot about where that point is. And so at the expense of regressing a little bit, I'm going to regress. All right? And my regression is going to be back to something that everybody thinks is really simple. And everyone will think, well, that's not really very hard. And I'll say, yeah, it isn't very hard. But when I get to something that actually is hard, then you're going to say, I'm totally confused and I have no idea what this is all about. And if I can't go back to that simple thing, then you'll say, I have no idea. You have nothing to compare it to, right? So I need something to compare it to. So we're going to start just with this concept of a function. I'm not going to get into anything else. I just want to talk about scalar functions for a few minutes. So imagine you just have I'm going to make it really simple. A scalar function of a scalar, right? So this is like math, calculus, pre-calculus 101. F of x, all right? What is f? Where f is a mapping from real numbers into real numbers. You all know how to do this, by the way, okay? This is why I'm regressing to this point, because you've seen this before, all right? So let me ask you. This class is about optimization. And when we talk about optimization, we are talking about the concept of minimizing or maximizing something. Why would we even want to do that? Can somebody give me a good reason why we would ever want to minimize or maximize something? Why? It can be anything, any reason. I don't care what it is. Just give me any reason in the world as to why we would want to do this. Yeah.
If it's a profit function, I want to maximize.
No, I'm not talking about functions. Why would we want to minimize or maximize something? Forget about functions for right now. Okay, I'll go back to the function in just a minute. Okay? Anything. You don't want to waste resources. Okay, that's good. You don't want to waste resources. What else? What you do this in real life. You don't realize you do it. And the reason you don't realize it, because nobody ever points it out to you. But when you plan your day, or you plan your week, or you plan your year, you're doing something. You don't realize you're doing it. What are you doing? You're doing optimization. Now, you're not formally doing optimization. You're informally doing optimization. Why do you think you might be doing optimization, or even implicitly? Because you don't just randomly do things any way you feel like doing them, right? You do them because you're like, well, I need to get certain things done, right? If you're a student and you're taking classes, you say, well, I have homework assignments. I need to get my homework assignments done in each of my classes. They are going to take me some amount of time to do it, but I don't want to use any more time than I need to, but I still want to do a good job, right? So I want to do it well, but I don't want to spend any more time on it than I need to because I have other things I have to do with my life too. I can't spend all my time doing my homework, right? I have other things I have to do. You know, I got to go grocery shopping, I got to eat dinner, I got to sleep. Well, maybe not sleep. But I've got to do other things that are going to consume my time, right? So we try to do this what we call efficiently, right? This is the concept of optimization, is to do something efficiently. But we have something that we run into all the time that makes it so that we cannot do things any way we want to. I'll give you an example, all right? I'm going to start with an extreme. This is all about extremes today, all right? So we're going to go to extreme. If I asked you, say, to put a grocery list together and go down to Publix and buy your groceries, and I said to you, I need you to finish your grocery shopping in 2 minutes. I've got a list of 100 items. I've got to go through every single aisle in Publix. Am I going to be able to finish my grocery shopping? Am I going to be able to get every item on that list? Why not? Why can't I? Why not? You know, I got to buy, I got to buy bread, I got to buy milk, I got to buy cheese, I got to buy I got to buy all kinds of other items, I got to buy laundry detergent, who knows? I got to buy plastic bags. It's a huge list that I've got, but I only give you 2 minutes. Can you do it? All right? Starting from your house or your apartment. You got to drive all the way to Publix. You got to finish your grocery shopping and get back in 2 minutes. Can you do it? Why not? Why can't you do it? What's that? It's not feasible, right? I have posed a problem that has no solution. You cannot solve that problem, right? What is it that makes it infeasible? The constraint makes it infeasible, right? I have made it an over-constrained problem. I've made it a problem that the constraint on the time makes it so you cannot achieve the goal that you want, right? So an optimization problem in real life cannot be done without having to adhere to certain constraints, right? If I say to you, now you have 3 hours to do it, now you say, yeah, I can do that because it takes me about 10 minutes to get to the grocery store. It'll take me about a half an hour, 45 minutes to go through the entire store, get all my items. It'll probably take me another 10 minutes to go through the checkout line, take me another 10 minutes to get back home and unpack everything, and maybe take me an hour and a half to finish the whole process, maybe an hour and 45 minutes. But now you can do it, right? Now the problem has a solution, right? So now what I've done is I've gone from infeasible to feasible, right? Now we're going to add another layer of complexity onto that, which is if I decide that I'm going to go to Publix and I want to use the least amount of time possible to buy my groceries, it would be a very poor thing for me to start with the shopping cart in the middle aisle of the grocery store, go all the way to one end of the grocery store, then go all the way to the other end of the grocery store, and then go back to one of these aisles, and then go back to one of these aisles, and then go back over to the other end, and then go back over here to get items, right? Nobody does that, right? They go through one aisle, then they go through the next aisle, and they go through the next aisle, and they traverse the grocery store in order. Why? Because it saves time, right? So there are lots of ways that I could do this, right? I could be haphazard about it and just buy my groceries in any order I feel like it, right? But I'm not going to do that because my brain is going to say that is a stupid way to buy groceries, right? It's going to say, I want to do this in an orderly way, right? So there are lots of solutions to this problem, right? I could spend 2.5 hours. I gave you 3 hours, right? I could spend 2.5 hours at the grocery store. I could spend 2 hours and 45 minutes. I could spend an hour and a half. But there's a solution in there that will allow me to do this in the least amount of time possible. So there are lots of feasible solutions now, right? But I'm not going to pick just any one of them. I'm going to pick the one that I think is going to save me the most amount of time. Now, is it truly going to save you the most amount of time? Probably not. Why? Because probably, in all likelihood, there may have been a slightly better solution than the one that you actually came up with. But it's pretty good, right? And it's certainly a lot better than all these other solutions that are just random, feats of craziness, which are not going to get you good solutions, and you're going to waste a lot of time. So we get into this whole thing. We got this function, right? And we want to be able to optimize it. But the problem is we have some kind of constraint. So we've got all these constraints that are going to come into play that we have to deal with. And given those constraints, we want to pick the solution that minimizes or maximizes that thing which we care about, subject to those constraints, right? Now, let's take one more. Let's go one step further with all this, which is that what is this thing that we're going to minimize or maximize? So I give you two problems, right? Let's suppose that I'm a really energetic person, and I like to traverse the aisles in the grocery store really, really fast, right? So I can speed through the aisles with my shopping cart, and I want to go and do this in minimum time. But I got my friend who's I'm going to bring along, and my friend doesn't like to do that. My friend likes to lollygag, right? He wants the minimum energy solution, right? He wants to use as little energy as possible and be able to get his grocery shopping done, right? Or her grocery shopping, depending on what you're talking about, right? Point is, you guys are both going to go grocery shopping, and I gave you 3 hours. So you're probably both going to get it done in 3 hours. But if your goal is to get it done in minimum time, and their goal is to get it done with the minimum amount of energy, are you going to wind up spending the same amount of time on your grocery shopping? Probably not, right? So this concept of minimization requires a metric, right? There's a metric associated with this. Your metric may not be the same as somebody else's metric. But the goal is the same. There's a task that needs to be accomplished. But the question is, what is the cost function or the performance index that you want to optimize in order to be able to achieve that goal, right? So it's not enough to just achieve a goal, because if I say, remember I told you, if I'm going to the grocery store, there are lots of different ways that I could get it done in that 3 hours, right? So I need to put a metric on there and say I want to minimize or maximize this particular performance index in order to be able to achieve my goal. If somebody else has a different performance index, then they're going to wind up getting a different solution from you. But you're both going to get optimal solutions relative to your performance index, right? But they're not going to be the same solutions, because one is optimized with respect to performance index 1, and the other one is optimized with respect to performance index 2. So all of this is what optimal control is all about. And it starts with this concept of minimizing or maximizing just a simple function. So now we're going to go back to simple functions. We're going to go back to this over here. Okay. All of you have done this. Where did you learn how to do this? What's that? Where? You've done it somewhere in your life, right? This can't be the first time you've ever seen a function minimization problem. Where? Did you do it in a class? Did you like have a job where you had to do this? I mean, something, right? You had to do it somewhere, right? So the question is, where did you learn it? That's what. So if any of you say, well, I don't remember where I learned it. All of you took calculus, right? Did you learn how to minimize and maximize functions when you were in calculus? Yeah, you did, right? So let's think about this. This is, it's amazing when you think about this problem. Everyone at some point today will be able to tell me the procedure. I don't want to know just the procedure. I want you to understand why you're doing what you're doing, not that you can do it. Okay? The fact that you can do it and you can plow through a bunch of equations is not the point. The point is, do you understand why you're doing what you're doing? So let's start with the procedure, though, okay? Because that's what all of you are comfortable with. You're comfortable with formulas, right? You want to open the joy of cooking, and you want to follow the recipe, and you want to bake a cake, all right? I don't want you to bake a cake. I want you to understand why the cake comes out the way it does, all right? There's a difference between those two things. If I'm going to bake a chocolate cake, I don't care. I know it's a chocolate cake in the end. I want to know why the chocolate cake tastes so good. What is it that you did that made it taste so good, right? That's the procedure, understanding the procedure, not doing the procedure, right? I can hand you the joy of cooking, and you can open up to chocolate devil's food cake, and you can make a devil's food cake or an angel food cake, right? That's not the point. The point is, do you understand why it came out so good, right? That's the difference. It's the difference between food science and cooking, right? So now I want the difference here between being able to run through formulas and understanding why you're running through those formulas. If I want to minimize or maximize function, let's make this really simple. Not only is this a mapping from real numbers into real numbers, let's just assume it's a smooth function. It's got all kinds. It doesn't have any weird kinks or discontinuities or anything like that in there. Just make it really simple. What did you learn how to do in calculus that would tell you how you're going to determine minima or maxima of this function? Calculate the slope. What's the slope? What's the slope? Let's see here. Here's a function. Here's my function. This is x. This is f of x. Okay? What do I do? Oh, a first derivative. Okay. What's the derivative? All right. So you take the derivative of f with respect to x, right? What do you do with that? Why? Why do I do that? Okay, so in order to determine the minimum and maximum, let's write this down a little bit more. In order, well, actually not in order. Say one way, I should say, one way is not the only way to determine minima, maxima of f is by setting df dx equal to 0. Okay. Why am I setting df dx equal to 0? What's that? Slope, okay. Here's my slope. Pick a point. Okay. So what is special about df dx equals 0?
Sign, the direction of changes.
Why?
So it's going to give you, if it does change sign, it's going to give you the local minimum or maximum.
Okay.
Not
If it
necessarily
doesn't
zero
change.
sign. It could be minimum or maximum. You have to consider
Okay.
the other.
All right. So, but wait a second here. Okay. Well, let's go back to this. So you said set df dx equal to 0. What is this criteria called? If I set df dx equal to 0, what am I going to do with that now? Right? I'm going to do something with it. What am I going to do with it? So df dx is equal to 0, right? But df dx is clearly not equal to 0 everywhere there, is it? It's only at certain places that it's equal to 0, right? So I set df dx equal to 0. What am I going to do now? I'm going to solve what? Solve this for x. So you're going to solve for x, right? That's what you're going to do. Now, what does that do? What does that tell you? So you started on this. What does that tell you? I'm sorry, I didn't hear you. What'd you say?
That we can find the possible value of x.
Right. You find possible minima or maxima, right? But not necessarily minima or maxima, right? Why? Why is it true, or why is it not necessarily the case that if I set df dx equal to 0, I'm going to necessarily give myself a minima or a maxima? What's another possibility? An inflection point, also called a saddle point, right? Because I could have a function, I'll just draw this on the side here. I could have a function that looks like this, right? df dx is equal to 0 there. But that's neither a minimum nor a maximum, right? So it's possible that I could wind up having df dx equal to 0 but not get either, right? So these are what are called critical points, right? These points, or I should say these values of x, are called critical points. Now, what do I do with these critical points? Okay, so imagine let x1 through xn be all critical points of f of x. So that means that all the points where df dx is equal to 0. So I found them all now. Okay? Now what? Now what do I do? Well, now you find the second derivative, okay? So now you compute the second derivative, right? And now what do I do?
If the number of critical points is limited, it's not infinity just to calculate.
No, it's fine. They're only n. I just kind of assume.
If you do the second derivative in some
No. What am I going to do with this second derivative? Before you tell me tell me the next step. What do I need to do with the second derivative? No third derivative. Just stick with the second derivative right now. What am I going to do with the second derivative? I'm going to check the sign on the second derivative, right? So what do I got here? If d second f dx second evaluated at one of these critical points is greater than 0, then what does this tell me? What's that? Then xi is a minimum. Well, we'll use this term loosely right now. Okay? And if d second f dx second evaluated at xi is less than 0, then xi is a maximum. But is it really a minimum or a maximum? What's that? Is this really a minimum? It's a local minimum, right? What does that mean? It means that locally, points nearby that point are going to have function values that are larger than the function value at that particular point, right? So if I take, for example, this particular case, where I use this point right here, right? Now, let's imagine, actually minimum is not a good example here. Let's do a maximum. Let's just make this function a little bit larger. Let's do this with the function. So it does that. So this is a maximum, right? It's a local maximum. That's also a local maximum, right? So if I find df dx here, it's going to be equal to 0, correct? If I find df dx there, it's also going to equal 0. If I take the second derivative here is going to be what? Less than 0, right? And it's also going to be less than 0 here. But is this actually the maximum of the function? It's not, is it? That one's the maximum of the function, right? So then I have to take another step, which is given all of the local maxima that I found, assuming this function is smooth, I have to figure out the one that actually has the largest cost, or the largest value of the function. That's my actual maximum, right? The other ones are all local maxima, not necessarily maxima. So to say minima is not right. It's a local minima. Now, it may also be the global, but I don't know that at this point, right? So the next step I have to take is I have to go through and I have to say, all right, which ones of these, if I'm looking at all the maxima, for example, which ones of these actually give me the largest function value of all these possible maxima, right? Now, that's all great, except for there's one problem. Now, let's take this particular case. Suppose my function looks like this. So here's my function. Okay? So it basically looks like that over there. Okay? I'm trying to replicate that. But I do something here. I tell you that you're not allowed to look here. And you're not allowed to look in this region. So this region's off limits. And you're not allowed to look here. This region's off limits. You can only look in here. So I'm going to call this value like x. Let's call it x min and x max is not good. Let's call it, I'll call it a and b. Okay? So now I've got this function f of x, which is a function of x. But I'm constraining you so that you can't look in here and you can't look over here. You're constrained to have to be between a and b. Now I ask you the question, what's the maximum? No. That's a bad question. I didn't ask the question. How are you going to figure out the maximum? Well, you got this great theory over here, right? This is awesome, right? You learned this in calculus. It can't be wrong, right? This is amazing. First derivative, second derivative. Everything's a plug and chug formula, right? That's what you've been taught. Everything can just be plugged into formulas. That is what you've learned. You've learned that life can be reduced to a sequence of formulas. And we're good. We don't even need to take this class, right? Because we don't need any of that stuff. I just compute first derivative, second derivative, I plug in, la, 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 boom, out spits the answer, right? That's what you've been taught, right? Correct me if I'm wrong, but that's what you've been taught, right? Now, I want you to do this problem. And I want you to come up with a systematic procedure to tell me what the maximum is. Not one that works for this particular problem, but one that works for all problems. Can you do it? Why not? You guys have taken calculus. I've taken calculus. The world is ruled by first and second derivatives, right? Everything falls into that category, right? Because that's what they teach you in calculus. Everything you need to know is on these 40 pages, right? Everything. Not just some things. Everything. Right? So the question is, what's missing from this? Why can I not do this using that approach? What's wrong with it? I didn't draw this line very straight. Straighten out the line.
What's wrong with it? I want the maximum. What happens when I compute the first derivative and set it equal to 0? What's the only critical point I will get if I compute the first derivative and set it equal to 0 if I restrict myself to being between these points A and B? I'm only going to get that one, which is clearly not a maximum, right? In fact, it's what? Minimum. So if I use that criteria where I set df dx equal to 0, this is going to be of no use to me in this particular case. Right? What have I just done? I've done something. And I talked about it a little while ago. I did something. I put a constraint on the problem. You can't do this any way you want to anymore. You've got to do it subject to my constraint. My constraint says that it has to be between A and B. Right? It changes. It's not the same problem anymore. What is it now? Intuition. We're allowed to use intuition. It's okay. Nothing wrong with using intuition. What is it that you can now ascertain given this graph that I have in front of you? What is the maximum of this new problem that I've just created? Don't tell me how you're going to get it. Just tell me what the maximum is. It's f of b, right? It's right there. There's my maximum, right? Maximum of f of x when f of x is constrained between, sorry, when x is constrained to lie between A and B is f of b in this case, right? Right? How'd you get that? It's okay if you just say, I stared at the graph and I got it. But just say that. Say, I stared at the graph, right? Stared at the graph. Now, what happens if I've got a really complicated function that's not just a function of a scalar? What are you going to do? You're going to get a surfboard and start surfing around the function and try to find that point, right? You're going to do that, right? Is that what you're really going to do? Are you going to get a you're going to get on roller skates and start sliding along on this like multi-dimensional surface, which could be in some really gigantic dimension, like x could be like, 500 dimensional, and you're going to go surfing around 500 dimensional space to say, well, I really want to find the minimum and maximum of this functional, and I want to do it by intuition. Doesn't really work, does it? Right? Doesn't work. Now, without going into a lot of mathematical mumbo-jumbo, we'll have plenty of mathematical mumbo-jumbo later, right? So we don't need it right now. Right now, what is a mathematical way of telling me that that, in fact, is the maximum? Can you describe it mathematically? This is just a scalar function of a scalar, right? It's not a complicated function. You told me intuitively it was f of b just by looking at it. Can you make that a little bit more rigorous? Not much more rigorous, but actually a fair amount more rigorous, but it's not that complicated, I should say. Okay, so that's almost right. What I know is, we know that in a neighborhood of B, right? F of what? If I say x, or if I say f of x plus delta x, right? Well, I say f of x plus delta x. Let's write it a little bit differently than that. So what I say is, I know that f of b is greater than or equal to f of x, right? In a neighborhood of B, right? But that neighborhood of B has a problem associated with it. What is it? What must be true about x in this case? Right. X has to be less than or equal to B. And it's probably between, say, B minus some delta, right? So there's something in here, right? Because if I make delta too big, then I wind up over here, right? If I start with x at B and then I keep subtracting, I'm going to wind up all the way over at A if I make this big enough, right? So x can be at most b, and it can be b minus delta, but if I make delta too big, I'm going to wind up close to a, and then this is no longer going to apply anymore, right? So what I've got here is I've got this. Now, is there another way to say this? Okay, so this gets into this concept of what we call, I'm going to write this down. It can be written either way, a maximum principle or a minimum principle. Today we'll just talk about it as a maximum principle since we're talking about maxima. Maximum principle. Okay. Optimal control, like any optimization subject, has these concepts of maximum, has this concept of a maximum or a minimum principle. What we're saying is this, is we're saying that, let's suppose, so let x be between a and b. X is constrained to be between a and b, right? So if I say that I want to maximize f of x where x lies between a and b, what does this give me? Let's look at the statement. The statement says, find the value of f that is the maximum over the allowable points of x, allowable values of x, right? What I want to know is I want to know the value of x that where that maxima occurs. You told me before that that maxima occurs at b, right? So the value of x at which this maximum occurs is x equals b, right? So is this going to give me the value of x? What's that? Is it going to give me the value? When I'm all done doing this calculation, what do I get? Do I get f or do I get x? I get f, right? It says find the maximum of f, right? It doesn't say find the maximum value of x. How am I going to get the maximum value of x out of this? Well, whatever that value of f is, I need to know what the value of x is that corresponds to that value of f, right? So what we do is we call this thing the argument. This is the argument of the maximum over a and b, of x lying between a and b, of f of x. What the argument means is f takes in an input argument, right? X in this case. When I say find the argument of the maximum, it says find the value of the input that makes f as large as possible over the possible values of x. This is a maximum principle. Now, if you look at this, you'll see this has nothing to do with derivatives. Do you see that? Right? This statement doesn't involve derivatives. It says find me the value of x that maximizes f, right, over the allowable region. It just so happens that if I'm back in this particular case here, where I have a smooth function, it's a function of a real variable, it gives me back a scalar, it does all these wonderful things, then I can use the derivative conditions. But I can't use the derivative conditions always. I can only use them sometimes. I have to know when I can use them and when I can't use them. This is a stronger statement than those conditions over there. Those conditions are more restrictive, right? In other words, when they apply, they really help me out a lot. But they don't always apply. That always applies, right? So it allows me to do more. But the problem is, it doesn't give me as much information, right? It gives me a lot less information. This just tells me what I need to do. It tells me I need to do this, but it doesn't tell me how I do it. That's why I said over here, this was the how. This is how we do it if we have this particular situation on our hands. But what we need to know is how can we do it when we don't have these nice simple situations on our hands, right? Optimization is a lot more complicated than just saying, oh, I want to minimize or maximize a function. And in the case of optimal control, which I haven't gone into anything with functionals yet, it gets even more complicated. So I'm going to finish this class today by just giving you a prelude to where we go as this course goes on. Optimization in the context of optimal control is not about determining points. Here we're determining points. You see that? X is a point. It's a value. It's a number, right? We take in numbers. We give you back numbers. In optimal control, the goal is to determine functions that themselves minimize other functions. So in other words, you say to yourself, well, I want to know what this function of time is that's going to minimize or maximize some performance index subject to a bunch of constraints. I want to know the whole function. I'm not interested in finding out about a point. I'm interested in finding about an entire path. I want to know the path that I need to take in order for something to happen. You do this all the time. You just don't realize it, right? When you say, you know what, I need to go to Orlando, right? And I want to drive to Orlando, and I want to get there as quickly as possible. Clearly, going from Gainesville to Tampa to Miami and then to Orlando doesn't get you there in the fastest amount of time. It certainly gets you to Orlando, right? Right? So that path is not the path you want to take if you want to get there as quickly as possible, right? In order to get there as quickly as possible, you get on Interstate 75 and then you go down the turnpike, right? That's clearly a lot faster than from Gainesville than going on this, tortuous path that goes from Tampa to Miami to who knows where, Key West, and then any other place you feel like going, Bahamas, So point is that there are lots of different paths, but you want to find the path that gets you there as fast as possible. So you want to find the whole function. You don't want to just find a point. You want to know what the whole function is that gets you there, right? Because that's what this is all about. That's what optimal control is about. It's about determining functions that minimize what we call functionals or optimize what we call functionals. A functional is a more complicated construct from this. A functional takes in a function and gives you back a real number, all right? So I just wanted to get everybody on the same page when it came to this, because this is something that I don't think ever gets explained the way I just explained it right now, even for a scalar function of a scalar, right? Because it's not always the case that you can just take derivatives and figure out things from derivatives. You need more than that. Okay? So we're going to start by just traversing this concept of a function for a lecture or two, get through some of the basic stuff, and then once we do that, then we'll move on and we'll get into optimal control and calculus of variations. There's a lot of stuff in this class. This class is a lot of fun. And like I said, a lot of it's just going to be what you put into it. If you put a lot into this class, you'll get a lot out of it. Okay?